Dear audience, dear chair, welcome to my presentation. My name is Julia Reisinger. I'm from TU Wien, Department of Integrated Planning and Industrial Building. And I'm presenting you the research results or the framework for integrated multi-objective optimization of production and industrial building design today. What are the challenges in integrated industrial building design? Meaning that variable production systems change a lot during time, but they meet very rigid structural systems, and the building is limiting the flexibility of the production system. And furthermore, there is the lack of integration and a coherent optimization of production and building systems or structural systems. Further on, if you make decisions in the early design phase, they influence the entire building life cycle actually, but to find a cost-efficient and ecological solution for an integrated design problem, there you need more than just one design solution or design variant. But variant studies are an elaborate process for, especially in integrated design. So the research I'm presenting today is conducted within the research project BIM-Flexi, where we developed a digital platform for design and optimization of flexible buildings for Industry 4.0. And the research goal is to increase the flexibility, the cost efficiency, and the sustainability of industrial building structures when changing production systems occur. And we solved this issue with a generative decision support tool, optimization and decision support tool, the PMOOD framework, which I'm presenting today. The PMOOD framework actually enables the integration of production layout planning into structural design. It enables automated generation of variants, the multi-objective optimization of production and building design, and finally it supports, or it acts as a decision support tool, which gives real-time feedback for lifecycle costs, lifecycle analysis, and the flexibility performance of industrial building structures. To give you a short overview, PMOOD means parametric multi-objective optimization and decision support framework. And in our previous studies and research, we have already developed the PLGO model, which is a production layout generation and multi-objective optimization model, and the POD, the parametric optimization and decision support model, which conducts structural analysis and the structural optimization, respecting the production layout and automatically calculating the life cycle costs, the life cycle analysis, and the flexibility of the structural system with regard to the production layout input. And what I'm presenting today is that we enhanced the POD model to the PMOOD model, and we integrated a multi-objective optimization algorithm into the model to automate the design process. Then overall, this is the PMOOD framework developed in Grasshopper for Rhino 3D. And the question we're asking in this paper I'm presenting today is, does this algorithm really provide feasible and satisfactory industrial building results? So the POD model gets enhanced by the evolutionary MOO algorithm, the PMOOD model. And here you see a rough framework of the parametric model in Grasshopper, or the script. And at the end, we integrated the multi-objective evolutionary optimization algorithm, which is a Pareto-based optimization approach. Actually, we integrated 3 different evolutionary algorithms, the CTAEA, the SPA2, and the SPA2 plus SDE, to see which one performs best. But this is not the focus of this research today. And it's all conducted or written in one C# component in Grasshopper. So the workflow, how it works is, first you have the input. Maybe I do it like this. First you have the input, and for the interface, you can input the building requirements, the property requirements, the production requirements, and then the PLGO model, the production layout model, automatically generates production cubes and the production process based on the input. It automatically conducts the performance evaluation. It evaluates the geometry, it evaluates the layout, and it calculates 3 flexibility objectives and 2 productivity objectives, which are then optimized with this evolutionary optimization approach. And it's semi-automated, the PMOOD framework, because after the layouts are generated, we want the users to select the layouts which he wants to further investigate in his study. So he can select the generated layouts he wants to import into the PMOOD model, and this is automated. So the PMOOD model, what it does is automatically generates the structural model, the cost model, and the sustainability model. It automatically evaluates the performance of the structure, and the costs and the resource evaluation and the objectives for multi-objective optimization are 5 flexibility ratings, the life cycle costs, and the life cycle assessment indicators. So, and then everything goes into the algorithm, and you get optimized building variants, which are already respecting the production layouts. This is, again, a manual process where you select the buildings you want to investigate, compare, or finally select, and then the data gets stored. This is just rough that you know what we are optimizing. So the variable parameters is the primary and secondary structure axis grid, and the axis field are variable. And the structural roof system, like truss and beams. So we integrated the timber calculation, steel and concrete constructions, and within set level you have the inner hall height, which the algorithm varies. The columns can be concrete or steel, and the bracing type. And also the model also applies retrofitting loads, which can vary, and different enclosure systems can be examined. And yeah, the production model varies the dimensioning of the cubes, the placement of the cubes. We are talking about the production areas, and the number of production scenarios. The objectives are already mentioned, life cycle costs, life cycle analysis, and flexibility performance. The flexibility performance, we published it in another paper, so we created our new flexibility criteria, where we are evaluating the retrofitability of the structure, the expandability of the structure for future expansion of the production system. We aim to maximize the hall height, the free inner hall height, minimize the columns inside the production areas, and enable to maximize the production scenarios. This is a quick demonstration of the parametric framework. Does it work? Yeah. So here's the PLGO model, and it already generated automatically the possible production layout scenarios. The more you go right, the less good they are rated. Then they are integrated into the model, and here we said, okay, we want to examine 4 different layouts within the building generator, and this is just where we show which layouts are now integrated. And then, these are not the best and optimized layouts, we have to say. This is already a little older video. And this is the C# component we developed. So you push start, and then yeah. Sorry for that. So you push start, and then the algorithm generates, like, I don't know, it depends on the design space or on the generation crossover mutation rate, around 13,000 variants, and collects the results. Here we also said, okay, we constrain the length of the hall, we just want to differentiate the width of the hall. And finally, you get all the results and all the examined building variants stored in the mask on the right, and it's already ranked. So on the top you see the best performing variant, and now we picked the 5th variant, and you always see real-time feedback to what it costs, what is the LCA performance, what is the flexibility performance, and so you can click through and do some interdisciplinary user study. Finally, you can also select the final solution and export it to a database, export it to BIM. So this is the developed multi-objective optimization window. So you see the visualization in Rhino 3D of the selected generated building variant. They are all ranked. And on the right, you see there is a weighting. So if there is a user, a building owner, who says, okay, I'm only interested in the cheapest version, so I put lifecycle costs to 100% and all the other criteria to 0, then the algorithm or the mask sorts it new and shows you just the cheapest one and doesn't try to find a trade-off between the goals. Yeah, and then you have the real-time performance feedback. You can see what it costs, what is the CO2 emissions. Exactly. So we conducted a user study testing if the PMOOD framework generates feasible design results. So we had 36 master students from architecture and civil engineering, which got together in groups of 2, we had then 18 groups, and they were simulating an interdisciplinary design process, and their task was to find the best solution for a hygiene production facility. So they had 45 minutes for the POD model, where they just manually changed the parameters and did some manual investigation of design options with no optimization algorithm. And they had the PMOOD model, where they got provided with the best performing solutions generated by the algorithm. Then they had to find 3 different variants, and which building solution has higher user acceptance and satisfaction was our question. So they chose one final variant and announced us if they preferred the building solution from the POD model or from the multi-objective optimization model. What were the results? The results were that 9 groups started with the POD model and 9 groups started with the PMOOD model, and then they switched to avoid the learning effect. So when the user started with the POD model, in 5 cases, they chose the PMOOD option. When they started with the PMOOD option first, when they clicked through the generated design variants, they mostly chose the option they designed afterwards in the manual creation process, which means probably they saw already really good results for them, and then in the POD, in the manual generation, they just adjusted them a bit. So 8 chose the final POD, and just 8 chose the PMOOD. And when we examined the performance results, which one they chose when the performance results were comparable, they rather chose their own generated option instead the one from the algorithm. And in one case, there was the performance results of the POD model were better, but they chose the PMOOD option as their final results, indicating that the algorithm found a solution they wouldn't have thought about that. And when we examined, okay, which structural roof combinations the users started manually and the algorithm provided, we see the results really differ. So the POD in blue sees, okay, students really wanted to investigate timber girder construction or timber framework constructions. But the algorithm provided them a lot concrete construction in secondary and primary access grid. And also timber girder with concrete, steel girder with concrete, steel framework with concrete was chosen by the designers from the PMOOD model, but wouldn't have been investigated in the manual alternative generation. Here you also see when they worked with their design intent and found their own variants, on the left side you see they chose rather big access grids, but the algorithms provide smaller access grids, So yeah, in manual creation, they rather choose more higher costs, but want to have more flexibility. Good conclusion. The major difference between the investigated designs with the POD and the PMOOD model were in axis grid materiality and roof structure type, so there were major differences. But we did not find a significant difference that the PMOOD model is preferred over the POD model. The PMOOD model replaces manual creation and reduces the time for design generation and exploration, but according to our study, would not provide better solutions for the user. And material combinations are a critical factor, which we've seen and which is not yet considered in the algorithm. The future outlook is we also coupled this model to a virtual multi-user virtual reality model. There the users can do the variance study and investigate the generated building options from the algorithm in virtual reality. And the next, this is already published, but in the next step we will investigate if the user experience and the user satisfaction is higher with a virtual reality framework than in Grasshopper. Thank you very much, and if you have any further questions.